Today is nice and straightforward. We're just going to be finding some partial derivatives. So I'm going to give you a function, and you're going to find the two partial derivatives, partial with respect to x, partial with respect to y. The idea is that if we're finding the partial with respect to x, x is the variable, y is a constant. If we're finding the partial with respect to y is the variable, x is the constant. So let's suppose that z is 3x squared y to the fifth. The important thing that's going on here is that this is a reading exercise. We want to look at how all these things are put together. In this example, everything is being multiplied. So the 3 times x squared times y to the fifth. It's just a big multiplication. The reason it's important to recognize this is that we do different things when we have a constant factor than when we have a constant term. So we need to recognize when we have a constant factor versus when we have a constant term. So if z is 3x squared y to the fifth, then the partial of z with respect to x, we're going to look at this in we have the 3x squared, that's the variable part. Actually, the x squared is the variable part. 3 and the y to the fifth are constant factors. So 3 and y to the fifth are constant factors. We take the derivative of the x squared factor, which is 2x. But with derivatives, we just multiply the constant factors. So the partial of z with respect to x has 3 and y to the fifth as constant factors. With respect to x, 3 and y to the fifth are constant factors. Now we would want to simplify this to 6x y to the fifth. There's the partial of z with respect to x. We'll do the same thing for the partial of z with respect to y. We'll identify what the constant factors are and just take the derivative of the variable factors. So the partial of z with respect to y, 3 is a constant factor, x squared is a constant factor, the derivative of y to the fifth is 5y to the fourth. So 3 and x squared are constant factors with respect to y. And like before, we would probably clean this up. 3 times 5 is something 15. So 15x squared, y to the fourth. We're making the distinction between constant factors and constant terms. Questions? Let's use that derivative of a constant is 0 thing. So let's make a new function. Let's suppose that f at xy is 3x squared minus y to the fifth. Want to do the same thing here, find the two partial derivatives, but we have a much different construction in this function. Now I have 3x squared minus y to the fifth. We're not including all these things with multiplication. They're not all factors. The first term is 3x squared. The second term is y to the fifth. So now if I want to calculate the x derivative, 3x squared is a constant, or sorry, 3x squared is our function, and derivative of 3x squared is 6x to the first. Y to the fifth is a constant term in this function. So the derivative of a constant term is 0. So minus y to the fifth is minus 0. In this problem, 3 is a constant factor, but y to the fifth is a constant term. And the derivative of a constant term is equal to 0. A similar thing happens when we find the partial with respect to y because of the way I set up this function. So the partial with respect to y of xy. In this case, the 3x squared is a constant term. The derivative of y to the fifth is 5y to the fourth. But it's really like 0 minus 5y to the fourth, because 3x squared is a constant term. With respect to y. So we just don't write those constant terms. First thing is looking at a variable term and reading it as a constant term. That's the tricky part. That's the first level of this skill. Making sure you can read constant term, constant factor. We could have combinations of these things. So for example, if we had g of xy is 3x squared y to the fifth plus 4y to the 4y. We'll just do 4y. I asked myself, come up with a integer, and I couldn't come up with one. I'll leave it at 1. So our read on this problem is going to go a term at a time. The partial with respect to x has y to the fifth as a constant factor, but 4y as a constant term. In the partial with respect to x, gx, xy. The y to the fifth is a constant factor, so the derivative of 3x squared y to the fifth is 6x y to the fifth, just like it was in that first example. And that's it. The 4y is a constant term. With respect to x, y to the fifth is a constant factor, 4y is a constant term. With respect to x. So it's like a plus 0 at the end. When we take the derivative with respect to y, we put a different read on the problem. Now I've got two variable terms. 3x squared is a constant factor, but I have two terms with y in them. So the partial with respect to y So in this problem, 3x squared is a constant factor. The derivative of 3x squared y to the fifth with respect to y is 15x squared y to the fourth, like it was earlier. And the derivative of 4y with respect to y is 4. So 3x squared is a constant factor. But I had two y terms in this function. So the derivative has two terms. Okay. Okay. How would you say it's going to be nice and simple? Take some derivative. We already know the rule. We're just upgrading them to deal with functions of more than one variable. A concern that you might have in the back of your mind, or I guess if you don't have in the back of your mind, but I'm going to put it there right now, inception style. I don't know why there's a big deal about inception. You don't need all this technology and like invading people's dreams. Just say something in someone's presence, and you can do inception on them. You know what I mean? So like the whole point was like, well, we got to make it think it was his idea. A suggestion plus time, they'll think it's their idea. A suggestion plus time plus praise will make them think it was their idea in the first place. You know what I mean? It's not hard. You don't need to invade people's dreams. Leonardo DiCaprio. Oh, yeah. And everybody was all, but it looks really cool. Does looking really cool work on a modern audience? When was the last time you went to a movie and like visually you were just like, oh, wow, this is amazing? Because I remember the last time it happened to me. It was in 1993. I went to see Jurassic Park. Nothing has compared to that since. I have never walked into a theater, even with like the better graphics, the better computer generated animation, even with all that, I have never seen a movie that had the same impact when I sat down in front of the big screen and saw Steven Spielberg's dinosaurs go wandering around. And I don't think I ever will. I think visually, I'm done. If you didn't see that first, because you're not ancient like I am, then maybe there's something else. But for me, personally, it's all over now. People were talking about how beautiful Avatar was. Still no Jurassic Park. I don't care what anything else, I mean, it was still pretty, but it did not have that same impact that Jurassic Park did. What a silly movie to be so important. Also, greatest marketing for Jurassic Park. All they had to do for marketing in Jurassic Park, they didn't have to show any trailers at all. The only thing that you saw in the trailer was the water in the glass go, and you hear the big thump. After you showed people that, you said, Summer, Spielberg, dinosaurs, and everybody just bought into it. You did not show them the dinosaurs. You know what I mean? Because now if you watch the trailers enough, you'll see the movie. You know what I mean? If any of you become executives in like 30 years, push for trailers where you don't show the whole movie during the trailer. Free professional advice. Come up with some more functions. New page, new rule. This one is going to involve all of our derivative rules are in effect. Product rule and chain rule in effect. Quotient rule, we don't need the quotient rule. You got product rule and chain rule. Quotient rule is just like extra. I think quotient rule knows it, so watch out. Might latch out into it. I'm relevant. It's like, well, no, you're not quotient rule. I got the product rule and the chain rule. I don't need you. You should keep quotient rule around though, because otherwise it already has some self-esteem. So product rule and quotient rule are always in effect. So for example, if z is, let's say, e to the 3x squared y to the fifth. This is a chain rule problem. I got e to the 3x squared y to the fifth. Oh wait, plus I had another term in the last one. And we're doing evolution. Here's an important function that you'll come across all the time in your career as a fill-in-the-blank. But what's going on here is going to be the chain rule. The derivative of e to the something is e to the something times the derivative of that something. And when we say the derivative of that something, there's going to be with respect to x and with respect to y. So the partial derivative of z with respect to x, the derivative of e to a thing is e to that thing times the derivative of that thing. And like we saw on the previous page, the derivative of 3x squared y to the fifth plus 4y with respect to x is 6x y to the fifth. The chain rule is always in effect. When we take the partial derivative of z with respect to y, we're still going to use the chain rule. The derivative of e to a thing is e to the thing times the derivative of that thing, which is going to be 15x squared y to the fourth plus 4. The chain rule is always in effect. When you take the derivative with respect to x of x to the fifth and come up with 5x to the fourth, you did use the chain rule. It just happened to be that the derivative of x with respect to x is 1. So this didn't show up, but we were using it. Here's a function that we have to read. Look at the construction of this particular function. I've got a 4y squared times the sine of 3x squared y to the fifth. So I have a product, 4y squared times the sine of 3x squared y to the fifth. The difference is going to, so we're going to read this as a product, which means the product rule. Except that 4y squared at the beginning is a constant factor with respect to x. So we don't have to use the product rule. Maybe I should have made it at x so I can use it that one. In either case, we're going to need the chain rule when we come to take the derivative of sine of 3x squared y to the fifth. That's definitely the chain rule. Chain rule is always in effect. But we don't use the product rule when one of the factors is constant. So 4y squared is constant with respect to x, so we don't use the product rule. 4y squared is a constant factor with respect to x. So we're not going to use the product rule for the derivative with respect to x. So the derivative of 4y squared times sine of 3x squared y to the fifth, 4y squared is just going to be a constant factor. So I'm just going to keep it 4y squared. The derivative of sine of something is cosine of that thing. The derivative of y, which is, or z, with respect to w, times the derivative of that thing, the derivative of w with respect to x. And the derivative of 3x squared y to the fifth with respect to x is going to be 6x y to the fifth. Just like it was on the previous page. You would probably want to clean this up. We got two monomials running around. You should put those monomials together. We got 24 x y to the seventh times the cosine of 3x squared y to the fifth. Any questions? When we read this problem as a function of y and hold x constant, I have a y function, 4y squared, times another y function, sine of y to the fifth. So since there is a product of functions of y, we need to use the product rule to take the derivative with respect to y. Because with the derivative with respect to x, I can read 4y squared as a constant factor. But for the derivative with respect to y, we're going to need the product rule. 4y squared is not constant. Sine of 3x squared y to the fifth, also not constant. So the partial of f with respect to y, I'll take the derivative of the first times the second. So 8y times the sine of 3x squared y to the fifth, plus the first times the derivative of the second. The derivative of sine of a thing is cosine of the thing, times the derivative of the thing. And now the derivative of 3x squared y to the fifth with respect to y will be 15x squared y to the fourth. Mainly so no one will accuse me of being creative. I just keep repeating this 3x squared y to the fifth. Now, once again, I've got a couple of monomials running around here, so I might want to clean that up. I'm still going to leave it as two terms, so 8y sine of 3x squared y to the fifth plus 60 x squared y to the sixth times the cosine of 3x squared y to the fifth. Here's the good news. Taking derivatives is always just going to be a reading exercise. Where are your functions? How are your functions combined? so that you know what rule to use and the order to use those rules. The only layer that we're adding to this is reading y as constant with the derivative with respect to x, and x is constant when we're finding the derivative with respect to y. I did mention that earlier that you want to keep the quotient rule around. But just because you see a quotient doesn't mean that you can automatically jump to the quotient rule. Sorry, quotient rule, you're just not going to be necessary here. The numerator and the denominator, we have a numerator and denominator, so we might think quotient rule. But notice that the numerator is just y squared. So with respect to x, the numerator is constant. The denominator just has x squared plus 1. So with respect to y, the denominator is constant. So the partial of g with respect to x we can just read this as y squared, a constant factor, times an x squared plus 1 to the negative 1. If I can read things as powers of my variable, then I do. I try to read things as powers of my variable. Of minus y squared times x squared plus 1 to the negative 2 times the derivative of the inside, which is always in effect of the chain rule. Y squared is just constant with respect to x. The derivative of something to the negative 1 power is that thing. I spelled 1 kind of wrong. To the negative 2 times the derivative of the inside, which is 2x. This is a little bit messy. I don't really worry too much about the negative 2 exponent. Negative exponents are just as good as anything else. The only reason you have to simplify when you're in algebra is because you're trying to get that point across. But in life, at this point in your mathematical career, you just leave your negative 2s, that'll be cool. But what I don't like is all these monomials running around. At least there's no constant in front of the y squared that has to get multiplied by the 2. But when you give me monomials, one of them has 3 and one of them has a 5, and you don't put them together to make a 15, I'm all like, come on, man, how lazy are you going to be? And you're like, dude, you didn't put those together in class. I'm like, well, I'm the teacher. I'm supposed to be lazy and make y'all do the work. But you might want to clean this up. Minus 2 xy squared times x squared plus 1 to the negative 2. If you're like, oh, dude, that looks awful, you can write it as a fraction. Minus 2xy squared over x squared plus 1 squared. But then we got that negative. Do we want that negative to look like it's on top, or do we want to put it in the middle? Now we're getting into style. And that's kind of up to you. Any questions? The partial with respect to y is even easier because it's just y squared. 1 over x squared plus 1, that's all constant. So the derivative of g with respect to y is just 2y times that constant. Question? It's a reading exercise. For the most part, if you're having trouble doing these problems, the main problem is going to be reading what the function is trying to tell you. The reason I point that out is a lot of times students will misinterpret what their problem is. They'll think they don't understand the process of taking derivatives. But that's the easy part. And x to the n minus 1, there's the sine is cosine, chain rule, product rule. That part you do understand. If you're making mistakes, it's probably coming down to not reading the function correctly. So while you're doing these problems, that's what your focus needs to be. Learning to read. I know I just accused you all of being illiterate when it comes to functions, but you're not illiterate when it comes to functions. I'm saying you're partially illiterate when it comes to functions. About looking at what the expression is trying to tell you. The advantage that you have is that they're mathematical expressions. So they are trying to tell you one thing and one thing only. Not like English, where English words are dependent upon so many things. English sentences, you could say the exact same thing and mean something completely different. Terrible. I don't know how we ever communicate anything. Or at the very least, I can understand why communication goes so wrong so often. Or to get like all nice sweatshirt. And then turn around and say exactly the same thing. Or did I? Nice sweatshirt. I didn't say the same thing, but I used the exact same word. Math will not do that to you. Math says, no, it's y squared divided by the sum of the square of x and 1. That's it. No one can misinterpret that, as long as we write things properly. So our job as mathematicians, and the huge advantage that we have is the expressions that we write mean one thing, and that's it. You can't read this in some different tone and think that it represents a different function. Math is just a better language. Any questions? Comments? Any thoughts? All right, that's going to do it for today. Go forth and practice your reading by finding some derivatives. That's it for today. I will see y'all on tomorrow. Everybody have a good day. And thanks for playing.